So in this video, we're going to go over some of Chapter 2 and Chapter 3. Um, there's only a few questions for each chapter. A lot of this information is good information, but might just be a bit much for this class. So Chapter 2 starts with the environmental factors and goes on to talk about um, how our building is affected by where it's located. And so as you page through it, you can see here it's showing you different. So up here, I will define like different latitudes, and based on the latitude of the building, the sun and everything will be affecting your building differently. So here they're showing in this diagram. Here's Minneapolis, Minnesota. That these lines represent, I believe, it's a heat affected the side that is hotter, depending on the orientation of the building in reference to north. North is up here. And so it's showing you in January versus July, and then at the different latitudes what the effect of the weather is on your building. And so what they do is they take this into account when they're designing um, window locations, building materials, how they're going to um, size the mechanical system, so the heating and cooling, based on where it's at. They'll need to know um, how it's located so that they can design the system to work the most efficient as possible. And so here it just kind of shows the different, uh, the sun in relationship to where our building would be. Um, and so there's some additional charts. And this would be good to know, particularly if you're thinking of going into architectural. But often this would be something that's figured out by the architects and the engineers and how to orient the building. So if you continue on in the chapter, it kind of shows you how to figure this out in some diagrams showing the sun. And the kind of cool thing about Revit is as you go through all of these things, you can actually turn on the sun path in Revit. So here's our building in Revit. And at the bottom here is the sun path. So I'm going to turn the sun path off and just show you. So here's our building. On the bottom, next to the scale, detail level, and the visual style, there's a sun path. If you select that little sun with an X in it and turn it on, it will give you this little compass and the sun in relation to our building. And then next to that, you can actually turn the shadows on. So if you just click that once, it'll turn the shadows of the building on. So the next thing you'd want to do, you can either do this with me, but this isn't anything we're going to do for our project, just as an example of what this chapter is talking about, or this part of the chapter. If you go to your Manage tab up top and select Location, it'll bring up the location of your building. It's default set to Boston, Massachusetts. But if you enter in our project address, the 6500 Pacific Boulevard Southwest for LVCC, this is it will actually we can actually get a closer idea of where the sun is going to be located in our building. So if you hit OK, it will adjust this however it needs to. And then since we have the shadows on, you can actually select this. This is what it looks like at 12 noon. And you can either enter the little arrows to try to see, the based on the times, and you can kind of see where the shadow is. So in our particular building, let's say we wanted to see what it looks like at 10:20 a.m. You can kind of see where the sun would be in location. And so engineers would use this to kind of gauge what they need to do and how they need to size um, all the systems. So here we can set it at 6 o'clock. Let's set that to 5 o'clock. By the end of the day, the sun is going to be mostly on this face too. So this building is going to be probably the hottest side of the building. And So you'd probably want to add canopies over here as well, since that it's going to get a lot of portion of the sun. So most of the day. So that's kind of a cool and pretty useful feature for designers to be able to see kind of in real time, based on a real location, the effect the sun is going to have on their building. And as you can see, when we turned it on, it knows that we rotated our view so that it knows the west is down here. And so that chapter kind of talks a lot about that, which is it's good to know, and kind of just be aware of. But it's probably not a lot that we'll do with it as a drafter. And if you keep going on, it's talking about the different climate zones, and talking about foundation depths. We've talked about that a little bit, depending on where you're at in the country. You would need to have a deeper foundation, or if you're in a drier area, you could have a shallower foundation. So we talked about this a little bit in the last term too, the foundation walls and the footings. Um, so if you keep going in that chapter, um, I it continues to talk about the thermal conditions and a lot of stuff that is valuable, but not probably not for us. But what is, I thought, um, good to know for us is the setting for the area for acoustics. So acoustics, so like our walls, so particularly in bathrooms or offices, you'd want to have a wall that does not transmit a lot of sound. And so the few questions we have in this one are concerning the walls and their STC rating, which STC rating, it will be one of the questions. It's a sound transmission class, and it provides an estimate of the performance of the partition in certain common sound insulation situations. So often in projects, you will get, and you'll see that the architect will define these walls need to have a minimum STC rating of whatever value they've determined. And so that's something to think about as you're designing, or if you're working for an architect, or depending on, whatever trade you're in. So like if you're working for a mechanical duct engineer, they would need to be cognizant of how they're running their systems through these sound walls, so that you'd want to make sure that any noise created by ducts, if they want this room to be somewhat sound resistant, then you're gonna have to account for that in your design. And so that the definition of the sound transmission class is just one that comes up a lot in architecture. And also too, acoustic partitions too. So an acoustic partition will be defined by the STC rating. Um, and so depending on, so like a sound wall might be a double wall, or it might have multiple layers of gypboard. But the other thing to think about in those too, as you're, is that they're also, if it has a particular sound um, rating, that they'll need to be um, they'll need to be sealed properly. So as you go through, and um, if you're, depending on what, what area of architecture or construction you're working in, you have to be cognizant of the fact that anytime you penetrate these sound walls, the same thing with the fire rated wall, there's special caulking and whatnot that will have to be applied to the wall if you do penetrate the wall with a duct or a pipe. And so um, here at the bottom here, it says that acoustic partitions need to have sealant around the edges and then any penetrations. Um, and also to it's dependent, that the STC ratings are dependent on the mass, the resiliency, isolation, dampening, and sound absorption. So depending on the materials that you use and the layers that you have, that's the things you need to consider. And so that's pretty much, I think, all what I wanted to cover in the chapter 2. You can kind of see here uh, an example of the wall where they're showing you that they have to have the sealant. So like if you were to make a sound partition wall type as an architect, you'd want to note it similarly to this, that it has to have the acoustic sealant or acoustic insulation and sealant that to kind of help reduce transmission of sound through the wall. And here's just showing other different types of things that you would do. So like particularly if you need to have insulation in the ceiling to make sure sound cannot transfer over the wall. And then more about just the acoustics and kind of describing how to reduce the sound in different areas. And so that's pretty much the gist of chapter 2. A lot of more thermal like stuff for the buildings, and then what I thought was probably more important for us is just understanding that in architectural design, what we might need to as a drafter be responsible for is making sure our wall types are properly called out for acoustics. Any place that you get a job at, they'll have standards and things like that, but it's something to be thinking of in the back of your mind, and wanted you to be able to have, that if you hear STC rating, that should ring a bell that has to do with acoustics. A lot of the stuff is obviously not going to be memorized. There's just so much information, but it's definitely good to be familiar and just kind of understand some of the terms that are going to be used often in construction. So in chapter 3, it's titled Resilience in Buildings. And again, there's a lot of good information in here, but not a lot that I thought we should necessarily need to go over or be tested on. But just some things to be familiar with. So this is really talking about how your building is in relation to any of the elements, whether natural or man-made elements. So it's going to talk a lot about seismic design. Wind does play a big factor in building. There's suction and things. When wind goes around a building, it actually will try to pull any finish off because it's kind of causing some suction at the corners. And so this chapter kind of goes over a lot of the different things concerning seismic issues, wind issues. Also, it talks about security and also crime prevention. And as you can see over here on the chapter headings. So what I thought was important in this video, here's kind of like a diagram showing all the different kind of issues that you'll have to and how they connect to one another. But one of the things that I thought important, particularly for us, is the safety issues in relation to seismic and wind resistance. So here under gravitational and lateral loads, buildings are required to withstand both gravity loads and vertical and lateral loads, which means, kind of like it sounds, that it needs to withstand loads that are affecting it from below and affecting it from above, both horizontally and vertically. And here it goes on to say it's from wind pressure applied to the building or base motions, which would be earthquakes. So I believe that'll be on the quiz. Often when we're looking at a building, the structural engineer will note that what the wind loads they're designing are based on, and they're in terms of 3-second wind gust speeds, so that they would, based on where it's located and the height of the building, that it'll be affected by 3-second gusts at whatever miles per hour. And that would go up, 6-second gusts at, 80 miles per hour or whatever, depending on whatever they've gone through and done the code research to determine. So to resist these loads, there's different types of systems that are combined to in a structure to resist these different loads. And here it says the lateral load resisting systems may be composed of a combination of moment frames, brace framed, and shear walls. And if you just take a look at this little diagram, and if you can guess which one, should be pretty easy to guess which one we're using in our building. So we'll be using the brace frame. So if you remember when we did the structural video, adding columns and beams, we added these brace frames, which exactly like it's defined, it's going to resist the loads from seismic, either from below, the lateral loads, or the wind loads from above, and live loads. It's going to keep the building from basically falling down, and it will also keep it so that it moves kind of as one piece, which is better than it moving independently. What happens if it moves independently from one another, if the floors are not tied in together? Then, well, just like in Jenga, if you move one piece one way and then the other piece the other way, it's going to fall over. So they really have to move as kind of one to kind of resist those loads better. So the moment resistant frame is just all these connections. There are specific connections that are defined by a moment frame, and basically they're all connected in a specific way. And there's no brace, but there has to be specific moment frame connections that transfer the load more uniformly. In this brace frame, you can see we have these diagonal braces at the corners, and in our building we put them in the middle. So we had them at the ends and then in the middle to resist the loads. And shear walls are basically like beams. The way they describe them are like beams that are cantilevered up from the foundation. So basically, a shear wall, it'd be a wall that is built in such a way that will actually resist, well, shear. And so it will either have diagonal X brace frames, or it will be have hold downs in the corner, which are basically hold downs or things that connect to whatever studs that there are to kind of reduce the movement. And they need to be nailed in a specific way or fastened in a specific way. Nailed for wood, and screwed for for a shear wall. For metal studs, they all need to. So the shear walls would need to be attached to the top and the bottom in a similar fashion, so that the load is moving in the same, moving together instead of separately. And it really just described this pretty good in here, and it's showing here how the building moves and how it really wants to kind of move together to keep it from falling over. And so this is kind of how their little diagram, I think, is pretty good, showing you how the building moves in like a seismic event. And similar to the wind loads, the engineers would have to design for 0.2 second for a short period and 1 second for a long period of ground motion. So like as an earthquake, a long period would be 1 second, and a short period is 0.2 seconds. And obviously they've got charts and things that, like if in California, the seismic would be a lot, they'd have to account for it a lot more than they would maybe in Illinois or something. So that's kind of a lot of what the safety in this construction talks about. Here's some more diagrams of kind of showing where and how the building is moving. And here it's showing here that if they're not, I think, connected, it can cause a collapse because they need to bend together. Everything needs to kind of move together in a seismic event instead of being separated. And here they're showing some, basically all the connections have to have a continuous path to the ground. And here they're showing some examples of typical steel connections that will help facilitate a kind of contiguous connections all the way to the ground. And here again, they're showing it in wood framing. So basically, this few pages up here are the sections I'm going to be tested on, kind of where I highlighted. And then if you continue on, again, I think it's good if you have time to read this, or at least skim through it and kind of familiarize yourself with some of the terms. But I'm not going to test you on all of this chapter. There's just a lot to it, and I just think there's probably too much in here to test on that. I mean, yeah, honestly, you probably won't remember, but definitely would be good to be familiar with it. And this chapter, they're talking about the flood, how to design for, in a flood zone. And they've got some details. Fire's another big one, where there's often in buildings where, we have to have fire rated assemblies and fire rated walls. And so this chapter goes on to talk about how fire affects the building and then how things should be sealed so that it's protected from fire. Because in here it's showing like the deflection of the steel beams as it's heated up and what happens to their shape. And so to protect that from happening, it does not protect it infinitely, but like they'll give an hour rating. So like, 2-hour rated assembly would protect it from fire for 2 hours. It's mainly to help give time for occupants to get out of the building. And then after the fire is security, and they go through how to design. So like we've done FBI buildings and other secure buildings where we have to design rooms that can withstand, and different walls that can withstand blasts or firearms. And so they have to be designed specifically to, if there's a certain size of a blast, or there's ballistic panels that they have to take into account for any kind of government buildings. And so there's design that's not super common. Maybe more common these days, as the different threats throughout the world. But that's another thing that this talks about, and that you can go through and kind of just know that there exists, that there will be different rooms and buildings are required. So we did a military base barracks up in Alaska. Actually, we've done a lot of kind of military things up in Alaska, and often exterior framing, not just like an interior room, has to be designed such that it can resist any kind of blasts. And so it's usually a lot of work as far as trying to design a wall stable enough that can basically be blown up and still be standing. So this kind of talks about that. Yeah, that's kind of cool. I didn't even notice this before. Showing the different capacity of explosives on these different cars. So here's some more about the ballistic protection and different bulletproof glass and ballistic panels. And same thing to do with same with ballistic glazing. So a lot of cool information, a lot of good information, but more specific information for than we want to really go over. And and again, you can continue to go through the chapter just to kind of peruse and look at sustainability versus how it is affected by the environment and other things. So that's pretty much chapter 3. There's some crime prevention things, and how to design, with those things in mind. And I don't know, there's a lot of good stuff, and I encourage you to read it, especially if you're thinking about going into a construction related architectural field. But mostly the questions will be in the safety under the gravitational wind loads and things. Those are kind of some of the things that are really common if you're working for an architect or an engineer, that you'll come across. So we'll have two quizzes this week, but they're really short. So just trying to figure out the best way to provide this information to you without, making you read an entire chapters of 90% of the information that you don't necessarily need or could even remember. So, but just highlighting the things that I think that are important and will come up, and you should be familiar with these terms working in these fields. So anyway, let me know if you have any questions, and yeah, that's it. Thanks.